if you ask that same query again, it will just return things from the cache. And the database itself will keep track of which data is dirty. For data to be dirty, that means you've written to it, and therefore the cache should be invalidated. The server will do all that for you. So there's some low-hanging fruit here. So especially, and we've experienced this even with the CS50 Core Shopping tool, where this past fall, things really started to grind to a halt with several hundred users using it all at once, because I hadn't made the best design decisions up front with regard to the table structure and the indices that we had. We didn't have the query cache on. So there was a number of things that in the middle of the night I was able to do without writing a single new line of code, just to get us through that week of shopping period without having to throw everything out, rewrite it, or even add to the server capacity. So realize there's some opportunities here. And then there's other technologies altogether. We can put up things. Redis can be used as an object-oriented store for actually storing more hierarchical data than something like Memcache, which relies on strings being the values. And there's many other examples in other architectures for this same idea. Any questions? And again, what's fun is you can, if you care, you can actually play with this stuff on the appliance. And if it is of interest for your student choice of iOS apps, realize you can have a web backend, and you can use the appliance or the cloud or some third-party host altogether for that. So after break, let's come back and chat about some of the database scalability issues and how they relate. And then we'll wrap up with a discussion on these topics. So without further ado, let's solve that database problem. So we introduced earlier in the story a database to actually store state, like our session information. But certainly more generally, if we want to store information about users and profiles and transactions and purchases and the like, we might very well need more than one database. Now, frankly, the simplest solution to scaling your database is often to throw money at it, right? Or throw CPU cycles at it. It's a lot harder, and requires a lot more thought to actually design your databases in such a way that they scale horizontally, though, as opposed to vertically. So here's some of the jargon in the industry. Scaling vertically pretty much means throw money at it. Instead of a gigahertz machine, get a 2 gigahertz machine. Instead of 2 gigs of RAM, get 4 gigs of RAM. And just scale the server up as much as you can. But there's a fundamental problem with vertical scaling based on that definition, which is what? Right. At some point, you will exhaust either your financial resources or the technological availability of hardware. You might max out at 3 gigahertz and 64 gigs of RAM, but there will be some upper limit, whether financial or technological. So thankfully, the world came up with this idea of replication, both in the world of MySQL and relational databases in general, but also in a whole bunch of other contexts. So typically in a web architecture, you will have multiple web servers, and those web servers have duplicate installations of your code. So they all have a /var/www/html directory, or they all have a vhosts directory inside of which is your website, and your PHP code and whatnot can be duplicated perfectly across all of those various servers. But the data that changes over time needs to be stored in some kind of database that allows it to read and write and change and delete and so forth. So if the problem is that a single server doesn't actually scale very well, well, you can have this master-slave topology, whereby you have one master server, as we've had thus far, but then you also hang off of it one or more slave databases, as they're called. And their purpose in life is to read data that's being written to the master so that they always have copies of the master. Now, what's the advantage here? In this topology, we have 3 slaves, 1 master. What's the value add then of introducing servers 2, 3, and 4 here? Because they seem to have some fundamentally distinct roles, at least semantically. That would seem to be the case if one's being singled out as master and everything else as slave. Yeah?
The read queries can get divided over 4 servers. Only write queries have to go to a single master.
OK, good. So if we leverage that assumption we made earlier, which was that reads are more common than writes, and this is quite often the case, not always, but in the case of Facebook and probably most websites that you've worked on for this class or others, they're probably a little more read-heavy than they are write-heavy. Certainly as they get popular, you get more readers than writers, perhaps. So if that's the case, you could just write your code in such a way that anytime you do an insert or a delete, or more generically, a modification to your database, you send those queries to the master. Whereas if you just want to do a select and some joins, you would do those on any one of the slave databases. So in this sense, you can optimize one server for writes, and then you can triple the amount of capacity you have for reads. So this sounds great. But what are some of the downsides or costs here? Yeah?
Can the slaves be read as they're written to?
Can the slaves be read as they are written to? Good question. Hopefully the database provides us with some form of integrity so that if we do a select while a query is being replicated from master to slave, that we're not going to get part of a row. And indeed, that's one of the things that a transaction-safe database would do, in that you're either going to read the whole row or none of it if you use something like locks or transactions. So in short, we can solve that. Other problems or costs that arise once we introduce slaves 2, 3, and 4 here?
You run into problems of sort of reading before a write has been passed.
Exactly. So what about consistency here, right? Even though you are replicating the data from master to slaves, that's got to take some amount of time, even if it's just milliseconds or microseconds. But in that window of time, suppose that the user has a second browser open, or suppose another user tries to pull up your profile roughly at the same instant you're actually updating it. That begs the question, what are those two users going to see? In fact, this too, you can occasionally see symptoms of this on Facebook, whereby you might update something and then it doesn't actually appear. And maybe when you reload, it's there, but it doesn't necessarily propagate instantly to that same browser window or another browser window. And that might not be a bug per se. That might simply be propagation delays. And in fact, even though in the ideal world this happens nearly instantly, it can still take several milliseconds, even a few seconds, if all of a sudden you get hammered with a huge number of writes. That might take some time for that buffer to clear and actually propagate to the slaves. There's actually a really interesting Facebook blog post from a couple years ago that I'll try to dig up and post on the lectures page, where they discuss the rollout of their East Coast data center. I believe they started with one main West Coast data center. And then for latency and scalability purposes, they, a few years back, added an East Coast data center. And the idea was to, one, be able to handle more users, but also decrease the number of milliseconds it took for East Coast folks to actually pull up Facebook content. If you have a server on the East Coast and you're on the East Coast, you can assume 10, 20, maybe 30 milliseconds of latency for the round-trip request and response to come back, which is pretty fast. If you're going cross-country, though, it can rise to 70 milliseconds, 100 milliseconds. So you could have that by having an East Coast presence, and never mind the implications for Europe and Asia and the like. So when they did this, though, there was an issue, because it was relatively easy, according to their blog post, to just do some replication of slave databases, or the equivalent, on the East Coast, so that you could have much more proximal and quicker reads, so you could access data more quickly. But writes, for technical reasons, were still pushed to the West Coast, as I recall. And I might be flipping the story, but I think this is the direction that things were going in. They still had all of their masters effectively on the West Coast, just because it was going to be hard to put masters at the time on both sides, or it was going to require at least more work. So the problem here, though, is that if I'm in harvard.edu and I update my Facebook profile, that update needs to get propagated to the West Coast. But then for performance, they wanted my reads and my reloading of the page and subsequent link clickings to come off of servers on the East Coast. So there was this delay potentially that you would see if things got backed up in the transfer process from West Coast to East Coast. And the article actually talks about some really interesting solutions they came up with, whereby I think one of their solutions was, when you do make an update to a page, say your profile page, they would plant a cookie in your browser that would say, hey, I updated something recently. And that cookie would have a lifetime of a few seconds or a few minutes. And that cookie would be used by their own load balancers to decide to keep sending you to the West Coast, at least for a few seconds, so that you see the very latest information, even though it's taking a few more milliseconds to get that round trip there and back. And then once that cookie expires and they assume that the replication has happened, then you get rerouted back to the East Coast. But there are these hoops you have to jump through. And Facebook is certainly not representative of most websites out there, but the number of technological problems that they actually face is really quite fascinating. And I will say, every year they bring out faculty and TAs to Palo Alto to talk about and see some of the technological problems they're working on. And if you do have an interest in scalability, whether it's hardware or software or networking, like Facebook and Twitter and a couple of their counterparts really work on some fascinating scalability problems that are really unprecedented until recent years. So what else is problematic about this besides potential propagation delays? What else can go wrong here? Or what's still wrong here? Yeah?
Will the writes still go to single master? So if that gets too full,
Yeah, so we've kind of just avoided the problem or postponed the problem a little longer, but if our traffic continues to rise, we still have, one, a bottleneck in the form of the master, and we also have a single point of failure, which means if he goes down, we can continue reading, but no one can update their Facebook profiles at all until we get that server back up. Now, one of the compelling features of master-slave relationships is that you can relatively easily promote a slave to master in the event that the master dies, and you could do that automatically with some scripts, or a human could intervene and actually tweak a configuration file, but at least it's a compelling feature whereby if, in the worst case, your master dies and your super fancy write server goes offline, at least within a few seconds or minutes you can promote one of the slaves because it should be a perfect copy thereof. But what else could we do here? Well,